Don't be shy. Which one? Sorry, say again, Kim? The charge? Yeah. Which page is that now? Huh? Well, in my book it might be different. Ah, yes. Can I guess which question? I'm guessing maybe you want to see question 4? Yes. Oh, yeah. See how I knew that? Okay, so charge and current, please. We'll have a look at that wonderful question 4. George, you ready? Charge and current. Yeah, question 4. Wonderful, wonderful Stephen question. Yeah. Right, let's have a look. Copper is used to form a wire inside a room, temperature 26.85 Celsius. And the diameter is 2 millimeters and the length is 1 meter and the density is 8.94 grams per centimeter cube. Let me draw that. So you have a copper wire. Here it is here. What's the length? What did I say the length was?
1 meter.
Yeah, so the length here, 1 meter. 1 meter. And what's the radius? Radius. 1 millimeter. And what's the temperature? 26.85 Celsius, which actually equals 300 Kelvin. What else do I tell you? I say there's a current. There's a current flowing in and coming out of 1 amp. And remember what 1 amp is. That's 1 coulomb per second. That's what we said an amp was. What else do we know? We know quite a lot. We know the molar mass of copper. What letter? We'll just write molar mass. Molar mass is 63.546 grams in a mole. What else do we know? We know the density. Now that's density is 8.94 grams per centimeter cubed. And also we know that copper has 1 free electron per atom. So you know, you did this in chemistry, you have free electrons in copper and they move around. Maybe you called it like a sea of electrons, ocean of electrons. Mm-hmm. Yeah. So I also tell you that the number of free electrons equals the number of copper, what's copper? Cu, isn't it? Number of copper atoms. So each copper atom has a free electron. I also tell you the charge and the mass of an electron. So the charge of an electron is the E, and that is minus. Remember, E is 1.602, or at 1.6 if you want, times 10 to the minus 9 coulombs, and the mass of an electron is 9.11 times 10 to the minus 31 kilograms. Okay, so I gave you a lot of info. Let's see what I ask you for. A. How fast are the electrons flowing through the wire? Hint. First calculate how many electrons are there. Then look how many flow out per second by looking at the right amount of wire. Okay, so it's quite advanced, but let's do it bit by bit. Now, I don't think you need to write this down, because all this information is in the question. So let's calculate it. First thing I want to do, I think I'd like to calculate how many atoms of copper there are. Because if I know how many atoms of copper there are, then I can know how many electrons there are, because the number of free electrons equals the number of copper. Okay? So I should work out how much copper I have. So I want to get the mass of the copper wire. The mass of the wire equals. Now if I have the formula density as mass over volume, then the mass will equal density by volume. And what shape is the wire? What type of shape is the copper wire? A cylinder. So what's the formula for volume for a cylinder? That's a sphere. That's a sphere. Yeah. Pi r squared h for the cylinder. Okay. Now, what's the density? I said it's 8.94 grams per centimeter cubed. You have to convert that into kilograms. So I think that works out to be 8940 kilograms per meter cubed. Okay, pi. The radius is 1 millimeter, so that's 10 to the minus 3 squared. And what's the length or the height? It's 1 meter. If you go back to the picture, it's 1 meter. Okay. Let's calculate this. Should this be a big or a small number if you have a copper wire? What do you think? Should be small, shouldn't it? The heck? Yeah, it's only, what's that, 28 grams? 0.028 kilograms. Okay, continue. How can I get the number of copper atoms? So I know the mass of copper, and I know its molar mass. So what should I do next? I should do a division, shouldn't I? So I can write this as 28 grams. And what's the molar mass? It's quite big, isn't it? It's 65 or 63. So the number of moles would be 28 divided by 63.546. Yeah? So divided by 60. Oh, well, I changed this into grams, didn't I? What the fudge? 28 grams divided by 63.546 grams. So there's about half a mole. 0.442 moles. Okay, this is looking good. How can I get the number of copper atoms? Times Avogadro. What number is Avogadro on my calculator? It's constant number. But it'd be nice if I can just use the calculator. 24 is the constant for Avogadro on mine. So if I multiply by Avogadro's constant, I get 2.66 times 10 to the 23. Copper atoms. So then how many free electrons do I have? Well, I said in the question they're the same. So I have 2.66 times 10 to the 23 free electrons. Hang in there, Siba. The sugar from the cookie is not giving you the energy you need, no? You should have had 2 cookies. Alright, continue. Yeah, continue. So, let's work out how fast these electrons have to move, okay? Think about it like this. You have 1 amp per second. So that means in 1 second you have 1 coulomb running through the wire and then coming out the other side in 1 second. 1 coulomb has to run through it. Now, that's how many free electrons I have. What is the charge of an electron? That's the charge is equal to E, which is equal to what's that now on my calculator? I think it's 27, isn't it? No, it's not. What constant number is E? 23. 1.602 times 10 to the minus 19. Yeah. Right, so we could calculate, you know, sorry, I keep changing my colours here. 1 amp equals 1 coulomb per second. How many electrons is that? Well, that's 1 divided by that E there. So that would be 1 divided by the E. So that's 6.24 times 10 to the 18 electrons per second. That's how many electrons have to move through the wire in 1 second. Yeah? Now, if you think about it, how many electrons do we have? We have 10 to the 23. And how many do we need to move through the wire? 10 to the 18. So, not all the electrons have to move through the wire. You know, because if they all move through the wire in 1 second, that gives us too much charge. We only need this many electrons to move. So it must be that the electrons are moving quite slowly. You know, if they all move very fast, and they'll all come out, and that's too much. Okay. So now we need to figure out how fast they're moving. Okay. I'll just pause for 1 second just to let you write all this down. Does everybody have this part? Yeah? Okay. And does everybody have this part? You all have this written down? No?
Why 1 divided?
Ah, yeah, because 1 electron is 1.6 times 10 to the minus 19 coulombs. And I want to have 1 coulomb. So if I want to know how many electrons I need, it's what I want, which is 1 coulomb, divided by how much each electron is. Another way to think about it, Matt, is if I multiply this number by this, you know, the number of electrons by the charge of an electron, I do get 1 coulomb of charge. Yeah.
It's the exam question?
Oh no, it's a Stephen question.
Oh,
Okay. Continue? Continue? Yeah. Okay, let's go down. So let's try and figure out how fast the electron is moving. So we'll do this by just looking at 1 electron. Okay, so if you have 1 electron here and it moves through, you can think of your distance, speed, time triangle. So what's the distance it has to travel? I'll just put in the numbers. What's the distance it has to travel? 1 meter. The speed, we don't know. At the time we do know, it's 1 second. So if 1 electron, so if 1 electron has to travel through 1 meter in 1 second, you can work out what the V is. It's 1 over 1, isn't it? Yeah? No, I've done something wrong there, sorry. I'm thinking about this the wrong way, apologies. Oh, I made this question too hard, didn't I? Made it too hard. Yeah, okay, so I think what I'll do is I'll just divide these two numbers. Where's it gone? This is how many free electrons I have. And this is how many electrons so this is what I have, and this is what I want. So you can see I have much more than what I want. How much more? I'll just divide it. How many times bigger is that? $42,628. That's how many times I have more electrons than what I need. I have 42,000 more electrons multiples than I need. So that means I don't want all the electrons to come out in 1 second. I only want a tiny amount to come out, like just the electrons in this piece. So they have to be moving so slow that in 1 second the electrons here can get out, but not the electrons back here. Because remember, we just said if they all come out, that's way too much. So how slow does it need to be going? Fairly slow, because it means in 1 second the electron can only move this distance. And how big is that distance? It'd be 1/43,000 of a meter. So the speed, distance, speed, time. The time is 1 second, so the speed is just the same thing as the distance. So if speed and distance are the same, it'll be 1/42628 meters per second. How big is that? That is small, right? 0.00120000. 2 meters per second. I could probably make this micro, huh? 23 micrometers per second. Oh, thank goodness. Oh, yes. So satisfied I got the same answer. Ah, very difficult. Very frickin' difficult. Don't worry. Not even in your worst nightmare would this come up in the exam. B and C are actually much easier, which we'll do now. Say again? Yeah, so you know your triangle distance, speed, time. The time is definitely 1 second. We want this much to come out in 1 second. So if the time is 1 second, that's distance and that's speed. What's the formula for speed? It's distance over 1 second. So you can see that speed and distance will be the same here. So what I'm saying is this distance, this number will be the same as the speed. So that's why I said V equals this. It's going to equal this distance. I need this much of the electrons to come out in a second. Oh, you don't look happy with this. No, tell me what you're thinking, please. Tell me what you're thinking.
I just don't know where did it come from, like the 1 over.
Okay. I'll use easier numbers just to make an example. Right. Can you all look up, please? See if I'll be strong. Be brave. Okay. So let's just use easier numbers to make an example here. Okay. Suppose in this hall I have 1, 2, 3, 4, 5 people. And suppose I have a door here, and this door can only let in 1 person per second. If all 5 leave in 1 second, then that's a problem. Too many people. So how many do I need to leave in 1 second? Only the guy at the end here. So how fast must they all be walking so that in 1 second only the last person gets out? Well, let's say this is 1 meter. How big is this piece? No, the whole thing is 1 meter. How big is this piece? Divide by 5. Why 5? You have 5 people. So it's 1 divided by 5. So that's equal to 0.2. Now, if you think about your triangle, distance, speed, time, what's the time? 1 second. We're talking about per second. So distance, speed. Right, what's the formula for speed? Distance over time. And what's the time? 1. So speed equals 0.2. So how fast are they walking? They're walking at 0.2 meters per second. This is the logic I'm using here. Now you might say, how did I know that it's 1 person? Well, that's what I worked out earlier. I worked out how many electrons I have, how many I want. So that's how I got the proportions there. So with people, it's easier to understand, but it's the same idea as over here with the electrons. This is what I'm saying, it's not easy. It's not easy because you have to kind of visualize a lot here. Shall we continue? Anyways, before I continue, there's one very simple point I wanted to make. When 1 amp comes out of this, the electrons are moving extremely slowly. Like you kind of have in your mind that the electrons are like flying out. Right? they're running out, right? But they're not. Like 23 micrometers per second. So the electrons, really what's happening here, it's very difficult to believe. You kind of picture the electron makes it to the end in like 1 second. But really, these electrons are only moving at 23 micrometers per second. So if you were to look at them, it wouldn't even look like they're moving. And this is quite interesting, that's why I put the question in, that when you have a current of 1 amp, which is pretty big, because I think, what did you say your phone was? It needed like 5 amps or so. So 1 amp is pretty big. The electrons are moving extremely slowly. So 5 amps would be like about maybe 100 micrometers per second, which is still very small. Yeah? Okay, continue. No, that's my point. You think it moves fast, and actually it moves very slowly. Yeah, I know. It's one of these science questions where the answer is opposite to what most people think. You know, if you said to people, do electrons move fast or slow in a current? They would say fast when it's actually slow. Because it's because of science fiction where you have like lasers and electricity kind of coming down quickly. You know, it's like this. Yeah. Right. B now. So, if the current is turned off, how fast are the electrons moving?
Well, all answers just A.
Just A. Yeah. Right. Now this actually is easier. I said that there's no current. No current. How fast are the electrons moving? No, actually, you would think not moving, but they actually are moving. Now the problem is, what formula do we use now if the electrons are not moving? So we have a cylinder, and there's all electrons in them, and they're moving around, but they're not moving in one direction. Because you know, with a current, they all move from left to right. But now they're just moving around in a sea of electrons, moving around freely. So what type of problem does this remind us of that we've seen? Yeah, the formula for the ideal gas. There's only one small problem. Is this cylinder made of copper a gas? No, it's a solid. But we can still use the formula to have a rough answer, okay? It's only a rough answer. It's not an exact answer like the last one. It's only a rough answer, okay? So if we were to say PV equals nRT, we have to make some estimations, okay? We actually know what the T is. What did I say it was? 300. And we know the R. We know the N. We know the V, don't we? And we can kind of estimate the pressure. So this formula is not particularly useful because we actually know everything in it. But what is it that we're looking for? We're looking for the velocity. There is another formula we can use. What was it? The 3/2 one. What was that? Is it 3/2 PV equals the average kinetic energy, wasn't it? Oh no, sorry, it's equal to the total energy. Wasn't that it? Yeah, that was it. I just can't remember if it was 3/2 or 2/3. Which was it? It was 3/2? I feel like it's... Anyways, it doesn't matter because it's only an approximation, so 2/3 and 3/2 aren't much different. Continue? Yeah? Right, so look. Do we know the volume? Yes. We could estimate the pressure. What would you say the pressure is? We could say it's 1 atmosphere, whereas really it'll be more than 1 atmosphere because it's solid. But we could say it's 1 atmosphere, roughly. So what's 1 atmosphere? That's 101,325. The volume is pi or, which is 10 to the minus 3 squared. The height is 1. Now what's the total kinetic energy? Well, that's the energy of one electron is a half the mass of an electron, the velocity of the electron squared. But how many electrons do we have? We have n electrons, which we worked out earlier. So, do we know the mass of an electron? We do. I gave it to you. Do we know how many electrons we have? We do. We know this, we know this, we know this, we know this. So can I get the speed here? Of course I can. This is actually much easier than the last question. So the speed will equal 3/2, 101,325 pi 10 minus 3 squared times 1 over. Now what did we say the n was? Did you write it down, the number of electrons?
2.66 by 10 to the power of 33.
Okay. A half. And then what did I say the mass of the electron was? Like 9.11. Yeah.
By 10 to the power of 30.
Okay, and then we need a square root here, because I just took this under and square root. Right, let's type this in. Uh, 1.5 times 101,325 times pi times 10 to the power of minus 6 over 2.66 times 10 to the power of 23 times a half times 9.11 times 10 to the power of minus 31. Before I press enter, are we thinking big or small answer? You're thinking small because the current is off and all of this type of stuff. No, it's huge. It's a big number. The electrons are moving at 2,000 meters per second. So the electrons, their speed is roughly 2 kilometers per second. Now, whatever way I did it last year, I got a totally different answer. The problem is I'm estimating, so maybe I estimated differently last year. But anyways, the difference is clear. When the current is on, the speed is in the scale of micrometers per second, and when the current is off, it's in the scale of kilometers per second. Do you see how different those two scales are? when we have a current, the electrons are moving at micrometers per second. When we have no current, the electrons are moving at kilometers per second. This is perhaps a shocking result for you. Would it be a shocking result? Yes, it seems totally crazy, doesn't it? The electrons, when they're free, they're moving much faster when they're, the current is on. And the reason is because there's a huge difference between a picture like this and a picture like this, where they're all moving to the right. Because this is unordered and this is ordered. Unordered pictures, they tend to be moving much faster than ordered pictures. Basically, this can do no work and this can do work. This is very unordered and this is very ordered. They're exactly the opposite. So because they're exactly the opposite, perhaps it's now not too surprising that something about them is exactly opposite, and in this case it's the speed. You know, when you think about it, what things can be opposite? Can their charges be opposite? No, they still have the same charge, don't they? They still have the same mass, don't they? They're still in the same volume, aren't they? But these pictures are complete opposite. So something has to be completely opposite. Not everything can be the same about the situation. So it turns out it's the speed that's exactly opposite. We go from extremely small to extremely large. Okay. Lastly, using your result from B and C, what can you say? You can say that ordered movement moves much slower than unordered movement. The way I think about it is like this. If you have an army walking, they walk quite steady, right? If you have a bunch of children running around in the playground, they run much faster, but also are unordered, right? That's what I'm picturing as the situation here. So the army marches to do work in an ordered, directed forward, slowly. Children in a playground aren't running anywhere to do work, and they're going very fast. You know, this is how I'm picturing the electrons behaving in the copper. The difference between army and children. Yeah. Okay, that was a wonderful question. A wonderful question. Well, we have a little bit of time. What will we do next?
Modulus.
Young's modulus, yeah.
So can I just see the...
Which part?
Oh.
Previous?
Yeah. Yeah.
Ah, yeah, 5 is a bit hard, isn't it? Let's look at 5 on Young's modulus now. I think you can get this from the video if you need it. Yeah? Okay, I'll have to scroll down so we can move on then. Okay, so number 5 here. You have a steel wire, a boy hangs 200 grams at the end of a 2 meter steel wire. Okay, so this is 2 meters and this is 200 grams. Did I give you Young's modulus for steel? What is it? Okay, and I tell you the radius, the diameter. He pulls it down 1 centimeter and releases, and the mass moves up. How long until it reaches its maximum height? So he stretches it down, he lets go, and it bobs up and down. Okay. What type of motion is this? Simple harmonic motion. So, what's the formula for T? For simple harmonic motion?
2 pi over omega.
No, the other one, simple harmonic motion. 2 pi root Oh no, it's gone, is it? Something over something. Yeah. Now, do you remember this formula now that you've seen it? You look like you have no memory of this. Are you sure you remember? Okay. Now that's the time. Wait, that's the time to go up and down. I just want the time to go up. So what should I do? Yeah, so divide by 2, so that's gone. Okay. Right. Do you know the M? Yes, it's 200 grams. Do you know the K? Do you know the K? You don't. What do you know only? You know the Young's modulus. Do you know the K? You don't. What formula has K in it? Yeah, that's it. So that's you have the formula F equals Kx. So you could replace K with F over X. Yes? Is that okay? Are you sure? Okay, let's continue. Pi root mx over f. Right. Do you know the f?
Yeah.
You do, yeah. Yeah, you could know the f. But the problem is, we need to think about it like this. We need to try and get Young's modulus into it. Okay, so if we think about Young's modulus formula, where can I go? Go here. Young's modulus is stress over strain. What's stress? That's F over stress over strain. No, that's right. It's F over A, and then strain is X over natural length. Okay, so if we look, do we kind of have that? Not quite. We're not quite there yet. I need to have an X over L and an F over A. That can be written as FL over XA. So I'm happy I have the F. Don't have the L. Don't have the A. Do have the X. Yeah, actually I'm happy because I have F over X and I need to have F over X. Great, okay, so I just need to have an L over A. Alright, that's not actually a big deal. So what I can do is I can change this into root X over F, that's this piece, M, okay, I'll put the M at the back, and I'll have an L here, an A here, an L here, and an A here. It's a dirty trick. You might, why are you saying it's a dirty trick? Well, these two cancel, don't they? So I'm left with XM over F, which is what I have here, XM over F. But what do these four now resemble? What do these four look like?
1 over E.
Yeah, very good, 1 over E. These four is 1 over E. So you can change this into pi root L over EA. Do you know the length of the wire?
Yeah.
You do. Do you know Young's modulus?
Yeah.
You do. Do you know the area? You do, and you get the answer for the time. That's a sneaky, dirty question. I agree. If you're thinking it. It's a bit of a Stephen question. It's not really so much an exam.
What do you say?
Huh?
What do you say?
Pi r squared. So you can change this into pi root L over E pi r squared. If you want, you can continue to simplify. That's pi over r root L over E pi. Let's keep simplifying for fun. So that is 1 over r root pi L over E. Right, that's the absolute simplest I can make this formula. So the answer is 1 over 0.5 times 10 to the minus 3 root pi times 2 over 200 times 10 to the, what was that, Siva, the Pascal for the Young's modulus for the steel? 10 to the 11, you said?
200 times 10 to the 9.
9. Okay, so that's the time. Whatever that calculates out as. Should be a very small number.
1 over all this or times?
1 over the radius multiplied by the root part. What you got?
6.285 10 to the power of -8.
Whoa.
I got 0.01.
Yeah.
Go ahead, Steve. What you got?
0.01.
I forgot the square part.
The square root. What you got, Steve?
0.0112.
Seconds. Yeah. Oh, my answer's off. Milliseconds. So that's. Oh, Stephen. I lost my M. I forgot to carry my M down. So there's an M all the way here. Yeah. Can you backspace and put in the M is 0.2. No, the 0.2 is in the root.
Yeah. 5.
Ah, there we go. Yeah. 5.01 is it?
Yeah.
Times 10 to the minus 3 seconds.
Yeah.
Yeah. Yeah, no, that's right.
I got a fusing them.
Show me. Ah, you typed it in wrong. That square root is on the top, not the bottom. Guy keeps getting better and better, isn't it? Chemistry next?
Yeah.
Good news is, in the exam, they don't usually make it this hard. What they usually give you is Hooke's constant. Then this is hard because I didn't give you Hooke's constant, I gave you Young's modulus. It's also hard if you forget the formula, 2 pi root m over k. Yeah. Is that formula in the formula book? Can you look at the back of your book and see?
Yeah.
It is? Last one on what page?
99.
Oh, good.
Yeah.
It is there. It's there. For a mass on a spring. It's the second last page of the formula book. It's up the top of the page. You see it? Helpful, right? Yes. Okay. Will we finish there? Or, yeah. How much do we have left to do in electricity? How many topics? One, two, three, 4, 5, 6, 7, 8, 9, 10. one of them's a double, the Kirchhoff one's a double, so it's 9 lessons. So it's 5. So we'll be finished in 2 weeks then. And we have 4 weeks left of classes. Great, so we'll be finished in 2 weeks and we'll do 2 weeks of revision. Sounds alright to me.